Hi everyone, I'm Jeff Parker. For those of you that I haven't met, I'm a faculty member here there, also faculty director at the Urban Institute for Energy and Society. So it's my distinct pleasure to welcome Ahmed Alahmed, who received his PhD in electrical engineering and computer science at Cornell, has had a number of really great internship experiences at places like NREL and EPRI, the Electric Power Research Institute, Rattle for sort of more of the commercial side. Won a number of Best Paper Awards, and is currently at my alma mater, MIT, at the Laboratory for Information and Decision Sciences. So what Ahmed's going to share with us today is a really important problem, which is this issue of kind of animating distributed energy resources. And if you think about that, those are growing. So we've got this portfolio of non-traditional assets that could be a really important component to accelerating the energy transition. That, to make that happen, requires a lot of things. It requires control technologies, it requires economics, it requires solving kind of complicated optimization problems. And so I'm really excited about your research program.
Thank you.
And I'll hand the floor over.
Thanks a lot, Jeffrey. Thanks. Yep. Thanks, Jeffrey, for the nice introduction and for hosting me. Many thanks to Tong, who is online, for also hosting me. And many thanks to Amos. She was really helpful in this trip. And I really appreciate the opportunity to be here. You guys are very lucky. The campus is amazing. So my name is Ahmed. I did my PhD in Cornell almost 4 months ago. And now I'm doing a postdoc at MIT. So very close to Dartmouth, I guess. My talk today is about distributed energy resources under net energy metering. So I understand that we have a wide audience here, so I'm going to explain all of these terminologies. So an example of distributed energy resources would be, electric vehicles, battery storage systems, rooftop solar, or any flexible consumption that you can think of in a household. And then net energy metering is really the gist of the talk today. So net energy metering is the most widely adopted policy to incorporate distributed energy resources into the electricity distribution network. So we're going to re-explain all of these terminologies. So my focus today is on the optimal decisions of households under net energy metering, and the adoption dynamics of distributed energy resources also under net energy metering. So this work is really heavily mathematical in nature, but for the sake of time, I'm going to focus more on the insights and main intuitions. And for those who are interested, I'm going to also attach the papers. So please feel free to ask me afterwards. And to make this more engaging, please feel free to stop me anytime to ask questions. This way it will be more exciting for both of us. So please stop me anytime. Okay. So just to excite you about the topic of net energy metering, this is a report that was published last year by the National Academy of Science on the role of net metering in the evolving electricity system. So actually the Congress asked or directed the national academies to come up with this report. And this really showcases the importance of net metering policy in the evolving electricity system. I have one slide to motivate all of my presentation, so hopefully it will be enough motivation. So really the main motivation behind my work in this area is that modeling-wise, it's no longer reasonable to treat electricity customers as passive entities that exhibit very price inelastic profiles, but rather they should be treated as more complex entities who are actually optimizers, self-interested. They look at what resources they have and they act on that. So I think that there has to be research that addresses the activeness of end users in distribution networks or electricity distribution networks. So the conventional electric grid is usually follows this scheme. So you have a centralized generation resources that generates power in bulk and then ship all of that power to transmission network, and then it gets distributed through a distribution network, eventually reaching the end users. So most of the generation in conventional power grids are dispatchable, meaning that you can actually control them and you can schedule them ahead of time. And in conventional electric grids, customers or end users are treated as lump loads. So they do not have any price elasticity, and they do not basically optimize their consumption based on their resources because they don't have a lot of flexibility to harness. So the main theme in the conventional electric grid was to measure demand or forecast demand, and then based on that measurement, you will dispatch generation. So the whole flexibility lies in the generation side of the grid. Because if you know Power System 101, generation and demand has to be equal at every instant. Otherwise, we'll have imbalances and blackouts and outages. So I think the conventional electric grid is rapidly changing due to multiple transforming trends. There are many, but I'm going to list what I think are as the most important three transforming trends. The first trend is the digitalization that is happening. So digitalization refers to the advancements in metering and sensory and telemetry devices that enables end users to be more active and more aware of the prices and the flexibility they have. The second trend is the declining costs of renewable and energy storage systems. So if you can see this figure, this shows the cumulative solar installations in the US between 2007 and 2022. So you can, and so this is shown by the bar charts, and then you have a line plot that shows the average solar system price. So you can directly see the correlation between declining solar prices and inclining levels of adoption of solar systems. And for example, between 2015 and 2022, the amount of residential solar installations in the US quadrupled. So this is basically driven by declining prices and also enabling tariff design, such as net energy metering, which we're going to explain in the next slide. So that is the second transforming trend. The third trend is the trend of electrification. So obviously, if you look at households right now, everything is being electrified. You have an electric vehicles instead of an ICE car, and you have electric ovens instead of gas stoves, and you have heat pumps, pool pumps. So a lot of the today's tasks are being electrified, so that adds a lot of burden to the grid. So all of these trends led to a futuristic outlook of the electric grids that are more distributed in terms of generation, and they have a bidirectional power flow. So as a customer, you might be buying electricity or selling electricity, because now you can adopt rooftop solar or any behind-the-meter generation resource and sell back to the utility. So there is a bidirectional monetary and energy flow in the future electric grids. And a lot of the generation resources are becoming more stochastic, and they are smaller units compared to the conventional electric grids and more ubiquitous. So given that customers are becoming more price elastic and more resource elastic. So the main theme of the future electric grid, or what we are advocating for, is that operators should measure generation, which is now stochastic. You need to forecast it. So you forecast generation in order to schedule DRs. So you can see that the image is flipped. Now all of the flexibility lies in the demand side rather than the generation side in the conventional power grid. And we're going to show in this talk a manifestation of how demand side can play an important role. I'm going to stop here for maybe 5 seconds to see if anyone has any questions. Yes?
Are you visualizing scenarios where the consumers are controlling the resources, or
Very interesting. So what I'm going to present today is actually giving prosumers the power of controlling their resources. But there are these models where you actually bring your own device to the utility, and the utility is going to basically control it and guarantee you a certain maybe benefit of that control. So yeah. Okay, so the outline of my talk is I'm going to explain this net energy metering policy or tariff design, and then I'm going to introduce the net metering X, which is a generalized net metering tariff model that captures all of the variations of net metering policy. And then I'm going to leverage this net metering X tariff design into the decision problem of a household. So here you will see the acronym or the terminology prosumer. It refers to a customer who can produce and consume. So this is just a silly name. They call it prosumers. And then I'm going to leverage the prosumer optimal decisions into the regulator decision problem of coming up with a price that achieves a certain objective for the population. So finally, with net energy metering, so really the high penetration of behind the meter generation resources is largely attributed to net energy metering policy. And in essence, you can think of, I think you can see my cursor. Yeah. So if you have a household, you have loads. Loads is D, and then you have a generation resource denoted by R, and then you are connected to Eversource, for example, your utility through this revenue meter or bidirectional meter. So under net energy metering, you are billed based on the difference between your gross consumption, D, minus your gross renewable generation. So basically, you are billed based on the net consumption. That is the difference between consumption and generation. So net energy metering has two main characteristics. Under net energy metering, you can self-consume your generation locally. So when you have rooftop solar generation, you can consume it locally. And then if your generation is higher than your consumption, you can sell this excess back to the grid. Okay? So that these are main characteristics of net energy metering policies. So, So the main reason behind the widespread adoption of net metering is that it is very easy to implement from the utility perspective. So you can just use the existing equipment to charge customers based on net metering. So it is a very low cost and easy implementation. And also from a customer perspective, it is very easy to understand. It is very intuitive that you install solar generation, you want to consume it first, and then sell any excess back. Simplicity of bills is a main axioms in the principles of public utility rates that were proposed by James Bombright in 1961. So mathematically, the payment or the bill under net metering 1.0, which is the generic net metering implementation, is given by this function P, which has the consumption as an argument and the renewable generation as another argument. And then you are charged based on the net consumption, the difference between D and R. And this is multiplied by the retail rate or the price that the utility designs. So if D is greater than R, if you are net consuming, then you are buying from the utility. If D is smaller than R, then you are actually selling back to the utility. So you can see that under net metering 1, the price of buying and selling is the same. You have equivalent buy and sell rates. So that's one part of the payment function. The second part is the so-called fixed charges. So a fixed charge is basically a charge that is independent of how much you consume. It is there even if you travel and never consume any loads. Okay? So this buy, the volumetric charge, can be either time invariant, so just a flat rate, or it can be a dynamic price or time of use price. It can be anything. Okay, so net metering 1 is very intuitive and simple, but there are many challenges with it. And it is, I think the reason that national academies wrote that book or report is because of the challenges under net metering 1. And they are huge, and they are causing a lot of contention, at least in the US. So by the beginning of 2022, 46 states revised their net metering tariff design, which means that there is a big issue with net metering 1.0. So I'm just going to list, I can talk about this for days, but I'm just going to list 2 reasons here. So the first reason that I think that net metering 1.0 is regressive is because it really proliferates utility revenue shortfalls. So the cost components that the utility face are 3 cost components: capacity costs or demand costs, variable costs or energy costs, and then you have fixed costs, which are the costs of servicing the customers and installing and maintaining their meters. But if you look at the customer bill, the bill that you pay, there's basically 2 costs. You only pay a variable charge that depends on your net consumption, and you pay a small fixed fee. So under net metering, you usually manage to reduce your consumption by 50% or net consumption by 50%, because now you have solar generation. And the issue is that the cost to serve you by the utility does not proportionally decreases, okay? So there are some utility revenue shortfalls, and they are huge. The second issue is the so-called utility death spiral. So death spiral refers to the phenomena that when you have a certain adoption level of rooftop solar, for example, this will lead to reduced energy sales. The utility will have less energy sales. And then this pushes the utility to increase their price to compensate for that loss. But increasing the price makes the adoption even more lucrative. So you'll have more adopters. And then you will run into this positive feedback loop until the utility cannot basically find a price that will achieve their cost recovery condition. Another issue is cross subsidies. Cross subsidies basically is that there are costs under net metering 1 shifted from customers who own solar to customers who do not own solar. We can talk more about cost shifts later. So SDG&E is a utility in California. They reported that net metering programs resulted in 3 billion cost shifts annually, causing an average bill increase of $200 per year for non-adopters, for customers who do not have solar generation, who tend to be less affluent compared to those who adopt solar. Any questions until now? Okay. So I'm going to go with introducing net metering X. So the motivation behind coming up with net metering X is that, as I showed, that many states are revising their net metering programs. So we came up with an inclusive parametric tariff model that captures the main features of this evolving net metering tariff design. So mathematically, the payment under net metering X is given by this function P, and you have buy plus, which is the price of buying from the utility. So that's called the retail rate or import rate. And buy minus, which is the price of selling back to the utility. And buy zero, which is just the fixed charge that is independent of the consumption. Okay? So net consumption is given by Z. If Z is greater than 0, then you are net consuming, which means that you are importing power from the utility. If Z is negative, then you are actually exporting to the utility. So you are a net producer. So this is how the payment function looks like. It's a piecewise affine function. So when Z is positive, you pay the retail rate. When Z is negative, you pay the compensation or export rate. And if you remember net metering 1.0, which I presented in the last slide, buy plus is basically the same as buy minus. So you have the same rate for buying and selling, and therefore the payment function becomes much simpler and much more lucrative to the owners of rooftop solar. Any question on net metering X?
Quick clarification.
Sure.
That's evaluated instantaneously, not the end of the month, right?
So there is an excellent question. There is a time component that I'm not discussing in this slide. It's called the netting frequency. So how often does the utility calculate your net consumption? And then after calculation of the net consumption, you will face a price, either buy plus or buy minus. So I think in California, they do this every 15 minutes. So you do not have a lot of banking period to use the grid as a giant storage. But I think in Nevada, they have like a 1 hour netting frequency. And in some states, they just have monthly netting frequencies or even annual netting frequency. So there is a time component that I'm not presenting. Yeah. Any other questions? Yes?
So for the first generation of NEM 1.0, it means that pi originally was just like the gross convection, but it didn't specify into the retail and like consumption rates, like import or export rates. It didn't take into account that.
Correct. So net metering 1, basically, you will face the same price whether you buy or sell. So regardless of your net consumption, regardless of Z, you're going to face the same price. Whereas under net metering X, these brackets are actually indicator functions. So if Z is non-negative, you're going to face pi plus. If Z is negative, you're going to face pi minus. Okay. Excellent. Okay. So this slide just shows the evolving net metering policy in the US. So we try to give main features for each net metering variant. So net metering 1.0, which is the one in New Hampshire, Vermont, and a lot of the Northeast states, it compensates you for exported power at the retail rate. So pi minus under net metering X is equal to pi plus. And usually you face a flat retail rate or time invariant retail rate. Under net metering 2.0, which was the case in California, it is now the case in Illinois and some other states. The compensation rate is slightly below the retail rate. So you buy at a rate that is slightly higher than the selling rate. And usually they mandate time of use for net metering customers. So if you adopt solar in your household, then you need to enroll under a time of use pricing, which means that the price changes maybe every hour. And net metering 3.0 is what is happening in California, and there is a great or huge pushback to flip this policy design or stop it. So under net metering 3.0, the compensation rate is very small. So you're almost getting nothing for exported power back to the grid. It is actually the compensation rate is almost at the marginal price of generating electricity. And they also have another components that are not very, I would say, solar customers friendly. So they have a more differentiated time of use. So the peak to off-peak period is even higher if you adopt solar. And you have shorter netting periods. So that's the netting or time component there. And the fixed charges under net metering 3 is higher. And even sometimes they are discriminatory. So if you adopt solar, you will face a fixed charge that is different than the customer who does not adopt solar. The last net metering evolution, which is something that is not yet actual, is the successor net metering policies. So these are less well-defined policies. But basically, they reduce how much you get out of your solar system. Okay, so this map shows the state of net metering in the states. And this is as of May 2024. This is rapidly changing. So I'm continuously updating this map. But you can see that a lot of the states are adopting net metering, or most of the states are adopting net metering. A lot of them are still using net metering 1.0, but there is a trend in moving toward net metering 2.0 or net metering 3.0. Illinois, interestingly, has the highest solar growth. And because of that, they're going to shift to net metering 2.0 this year. Because if you have a lot of solar generation under net metering 1, then you have all of these challenges that we discussed. So you need to consider a successor net metering policy. And net metering 3 in California and Arizona almost stalled the renewable adoption in those states. Okay, Any questions on this?
I missed what SMC stands for.
SMC.
What might this one do?
Oh, yep. Yeah, so SMC is, sorry, I did not define that acronym. SMC is the social marginal cost. So social marginal cost is a few cents above the wholesale market price. Yeah. Yeah, Ben?
Yeah, I was curious about for the net management
Mm-hmm.
how willing must be people to, unless forced, how must be people to actually adapt to this, unless they are forced by mistake?
Excellent question. What motivates them is that they will couple their solar with a storage system. So if you couple your solar system with a storage system, then you are not desperate to sell back your generation, but you can really keep it behind the meter and then use it whenever you need it. So you're not going to be really affected by this evolving net metering policy if you couple your solar system with a storage system, basically. So yeah. Okay. Presume. Yeah.
On that thread a little bit.
Sure.
From the point of view of the system, is that something you would want to incentivize, or is that a problem?
So in California, they are justifying moving to net metering 3.0.
Yeah.
To the reason behind that is to encourage prosumers to couple solar with storage. So yeah, that's an argument I can buy. So yeah. So now with a slightly mathematical maybe formulation. So now we know what is this net metering policy. We know net metering X. So we want to look at if we have a household, just this is the most simple case. You have a household, you have flexible loads, and you have rooftop solar. And you are facing the utility under net metering tariff design. What are the optimal decisions for this household? How do you optimally schedule your resources? So the first question we run into is how do we characterize the benefit of this household? You know, what is your benefit of consuming a certain profile? So we used something called the surplus of consumption given by the function S. So we define the surplus as the difference between the utility of consumption, so how much satisfaction you get from consuming a certain device bundle, minus the payment under net metering. So that is our objective. And then we have energy balance constraint, so the net consumption constraint, and then you have a budget constraint, and also we have consumption limits constraint. So you have certain flexibility that you are willing to do. So just some notations. I'm gonna denote the optimal consumption, so the optimal solution, by D star, which is a function of the renewable generation. And I'm gonna denote the optimal value or the surplus under optimal consumption by S star. Okay, so now with some schematics. So if you adopt net metering 1, if the utility adopts net metering 1, then we wanna see how your optimal consumption would look like. So if you are a consumer, if you are a customer who doesn't have solar, so notice that I'm plotting against the renewable generation. So R is the renewable generation. If you are a consumer, then you don't have any solar, so your consumption will be basically independent of the renewable generation. You don't have generation at all. If you are a prosumer, if you have solar, under net metering 1, it turns out that your consumption is not going to be a function of the renewables, because you basically don't care if that renewable is locally consumed or sold back to the utility. You get the same value for local consumption and selling back. Okay, so that's why you have a straight line. The consumption is not a function of the renewable generation. Here, this is the plot of the surplus. If you are a consumer, obviously you don't have solar, so it's just a straight line. If you are a prosumer, then your surplus increases linearly with the renewable generation at a rate of pi plus, or the retail rate. So this is the case under net metering 1.0. Things get much more interesting under net metering 2. So under net metering 2 or 3, you have two prices. You have buy plus and buy minus for buying and selling. I'm replotting what happens if you are a consumer, if you don't have solar. We found that the optimal consumption policy is a threshold policy. So you do solve for two thresholds, D plus and D minus. Those two thresholds partition the range of the renewable output into three zones. And the first zone is the net consumption zone. Second zone is when the renewable falls between the two thresholds. We call this the net zero zone. And the third zone is when your renewables is high enough to be higher than the high threshold, higher than D minus. Then this is called the net production zone. The optimal consumption looks like this. So it is a monotonically increasing function of the renewable generation. This is really intuitive. It says that you're gonna increase, or you are inclined to increase your consumption when you have more supply. When you have more generation, you're gonna consume more. So you can see that the consumption is static in two zones. It's just a straight line. And then the consumption is dynamic in the third zone, in the net zero zone. And it turns out that in the net zero zone, your consumption follows exactly your renewable generation. So you will match your consumption to your renewable generation. Now, if we plot the surplus, S star, then if you are in the net consumption zone, the surplus increases at a rate of pi plus, obviously, because you face pi plus from the utility. If you are in the net zero zone, the surplus has this concave shape. And then if you are in the net production zone, the surplus has a slope of pi minus, but it is increasing. So let's say that you are not an active customer. You want to stay passive, or you don't have the equipment to intelligently manage your system. Then you're going to be a passive customer. So your consumption is going to be the same as your consumption if you don't have solar, but your surplus is going to be suboptimal. Okay, so that gap between the surplus there and the S prosumer zero is how much you can achieve if you become active. This is your net consumption, so the difference between consumption and generation, and this is your net consumption if you are a passive customer. The most interesting zone is this net zero zone. We were not expecting this zone to emerge at all. So I think I'm going to try to explain the intuition of the emergence of this zone. So basically, your generation is higher than D plus, higher than this threshold. Then you have two options. Either you can continue consuming business as usual, and you will run into the net production zone, so you're going to face pi minus. Or you can increase your consumption at this rate and still gain at a level that is less than pi plus, but higher than pi minus. So you will continue doing that until your generation hits D minus. And then when it hits D minus, you have no option but to be a net producer. You're going to sell the excess back to the utility. Okay? Any question on this?
When you say you have no option at that point,
Yeah.
you still would have an option to consume power.
Correct.
That just wouldn't have much marginal utility.
Exactly. Sorry. Yeah. So you still have the option to increase your consumption, but that doesn't get you as much surplus as if you sell back. So yeah. Any other questions? Okay. So we also had some results. Oh, this one here shows how you compute the thresholds, D plus and D minus. The good thing is that both of these thresholds are independent of the renewable generation. So basically, you can compute them a priori, and they are very simple to compute. So equation 1 shows how you compute the two thresholds. They are basically a function of the inverse marginal utility of the household and the utility parameters, the utility prices, which are known to customers. And in the net consumption zone, your consumption is based on equation 2. This is D plus. Production zone consumption is equation 3. And then when you are in between, it is more slightly complicated to compute the consumption, but it is still manageable. We have a proposition here that says, there is a load priority ranking rule. So if you have a lot of renewable generation, then you will schedule the devices that are less important. If you have scarcity in renewables, then you might defer, exercising or charging your EV or operating your pool pump. You will wait until you have a lot of renewable generation. So there is a priority ranking for each load based on how much renewables you have behind the meter. This is the last maybe theoretical result I'm going to present on this topic. So we did some comparative statics. We found that when the prosumer maximized their own surplus, which is a self-interested agent objective, it improves the system efficiency by locally consuming the renewables instead of selling them back. And the optimal consumption is intuitive, as I mentioned, as it responds to increasing local generation by also dynamically increasing demand. And reducing the sell rate enlarges this net zero zone. So if the sell rate is lower as you go to net metering 2, 3, or successor net metering, you want to keep as much renewables as you can behind the meter. You don't want to sell back. And optimal consumption reduces negative payment because you do not sell as much to the utility. Okay, so this was the simplest case. We only had one device that I showed. I'm not going to show the multiple devices case, but we also worked on adding a battery to this system. And turns out that the problem becomes much more complicated unless you do some assumptions to have some analytical results. So the problem here is to co-optimize the flexible demand, so EV charging, heat pumps, and other flexible demands, and the energy storage resource by charging and discharging your storage, and again, under net metering. So we formulate this problem as a stochastic dynamic program that, again, maximizes the expected operation surplus. And so we have a lot of constraints here that are storage related. You have the state of charge of the storage, you have the capacity of the storage, and you have the charging capability of the storage. So to circumvent the exponential complexity of the dynamic programming solution, we proposed a closed form and linear computation complexity co-optimization algorithm based on a relaxation-projection approach. I'm going to share the paper because I think that this is going to take more time. So we showed that if you do this relaxation, actually the optimal policy, the optimal co-optimization policy, is very similar to the optimal policy when you don't have a storage. So you still have a threshold policy, but instead of having 2 thresholds, you have 6 thresholds. And you can see that we preserve, monotonicity is preserved, so you increase your consumption with renewables, and also you increase your storage with renewables. And we showed some sufficient conditions for the optimality of the proposed solution. And by doing some numerical studies, we showed that basically the solution gap is very small if you don't have those assumptions. Okay, so I'm going to show one simulation results here. So the top 2 figures are when you have flexible consumption and solar. The bottom figures are when you have flexible consumption, solar, and battery. And what we are plotting here is the reverse power flows, so how much power you export to the utility company. So if you are a passive customer, you can see the top left figure. If you are a passive prosumer, then you export this much. So the darker it is, the more reverse power flows. And if you become active, because there is this net zero zone, so you consume more renewables behind the meter, you can see that the reverse power flows are reduced. When you install a battery, this is even more clearer. You can see that the reverse power flows are really minimized. Okay. Any question on this? Okay. So this is the last section of my presentation. How many minutes do I have, Jeffrey? Sure. Yeah. Sorry, could you repeat the question?
So what are you assuming about pricing? How are these prices set? So you're looking at the consumers reacting to the prices are also time varying?
Yes. So you have a time varying prices. The prices are not uncertain. For residential customers, the prices has to be announced ahead of time. So the prices are known, deterministic. They might be, time varying, But what we are assuming is that the sell rate is always no higher than the retail rate. So buy minus is always smaller than buy plus, which is the status quo. I mean, otherwise utilities will be really in trouble. So that's the only assumption we're making. Obviously, we have in the optimal policy I showed, we have some assumptions on the shape or the functional form of the utility function. So we assume concavity and other assumptions of the utility function. Otherwise, we won't have maybe some reasonable analytical results. Okay. So finally, now we know what is the optimal decisions of households. We're going to use those optimal decisions into a pricing process that is done by the regulator or the distribution utility company. So we assume that distribution utilities solve the so-called Ramsey pricing problem. So under Ramsey pricing, the objective is to maximize the welfare of the population subject to a revenue neutrality condition. So utilities are usually regulated monopoly, so they cannot achieve profits beyond what is set to them. So this is why we have this constraint. And this S is the customer surplus, which is defined as the sum of prosumer surplus and consumer surplus. And then this gamma is the fraction of prosumers in the system. And this is the environmental benefits achieved due to the adoption of solar generation. And then we have the surplus function of the utility company, which has the payment the utility collects from prosumers and the payment the utility collects from consumers, minus the cost that the utility incur to service those customers. So we analyzed 3 net metering cases: net metering 1.0, which is the Californian version of net metering 1, net metering 2.0, again the Californian version, which has a time of use component, and net metering with a social marginal cost compensation, which is almost a compensation at the wholesale market price. So we had some performance measures to see how the rate really performs. So the first measure is the social welfare, the aggregate surplus of the population. The second measure is cost shifts. So cost shifts is the difference between the bill savings that the household achieves minus the avoided costs that the utility achieves. So how much the utility is losing by you having this solar system under net metering. Because eventually that cost shift, that lost revenue is going to be levied on those who do not have solar. Then we have payback time, system payback time, or rooftop solar payback time. We have market potential, which is basically a function of the payback time. So here I want to show this figure. The top left one shows the social welfare of the population under 3 net metering implementations. The x-axis is the percentage of adopters. So you can see that under net metering 1, and net metering 2, you have an increasing social welfare, but then after you hit a certain adoption threshold, the welfare drops. And until you reach a point, that end point of the curves is when the utility run into the death spiral, because they cannot come up with a price that achieves that Ramsey pricing constraint. The reason for this drop in welfare is when you dissect this into consumer surplus and prosumer surplus. You can see that as the adoption increases, consumers are really hurt. Their surplus significantly decreases. Whereas if you are a prosumer, your surplus significantly increases. So the social welfare is kind of the balance between the prosumer surplus and consumer surplus. So you can see this interplay between those 2 customer categories. The top right figure shows the retail rate. So under net metering 1 and net metering 2, the retail rate just goes crazy, and that's why we run into death spiral. If you adopt net metering 3.0, then you can keep the retail rate at a reasonable level. So if you know a bit about the Californian systems, their retail rate is 50 cents per kilowatt hour, which is huge. So that's because they had net metering 1.0 for a long time, and the adoption really increased in the net metering 1 and created a lot of revenue shortfalls issue. I'm going to skip this figure. This figure shows the market. This figure shows the cost shifts. So net metering 1 has a lot of cost shifts, and then as you go toward net metering 2 and net metering 3, you can minimize the shifted costs. I'm going to skip this too. So all of what I showed in the previous 2 slides is a short-run analysis. So we consider that the tariff, that the solar adoption so we consider that the tariff is basically exogenous. But in the long-run analysis, we incorporate the solar adoption rates, the solar costs as endogenous variables. So this is one of the figures we have in the paper where we plot, for 20 years ahead, and then we show if you change by minus, how is the percentage of adopters is going to look like in the next 20 years. The same goes for cost shifts. Also, we can comment on that on the long-run outlook. Okay, more figures. Here, this is my last, the slide before my last slide. I want to say that this is the first part of my PhD. I worked a lot on standalone customers, so single households autonomously facing their utility. But I also worked on large-scale systems. So this is called an energy community, where you have multiple customers pooling and sharing their resources together as a single entity behind the utility. So you can really see the value of being an active customer under larger scale implementations, like energy communities, for example. And also I worked on DR aggregation, which has a different flavor than energy communities. So DR aggregators are profit maximizing entities. So there is a different objective there, whereas energy communities are profit neutral entities. So with that, I'm going to go to the concluding remarks of my talk. So net metering X is a convenient, natural model for existing net metering policies and the proposed successors. The optimal prosumer consumption without storage has a simple 2-threshold policy that lends itself to a highly scalable scheduling solution. That's why we went into larger scale implementations. Optimal prosumer consumption not only maximizes the surplus of the household, but also improves the overall efficiency of the system and reduces cost shifts. And a key takeaway point of net metering policy evaluations is that while net metering 2 and the successor net metering policies address different levels of equity and stability concerns, such policies can potentially have negative impacts on the adoption decisions. So you definitely have a trade-off between economic efficiency, like social welfare, equity, like cross-subsidies or cost shifts, and technology sustainability or adoption levels. So you have those trade-offs, and you need to be prudent in designing the net metering policy that hits the sweet spot between these different performance measures. And I think that's all. Thank you.